I'm going to present something where there's only one quantum slide, so the Q here is not going to be very relevant for my talk, but anyway, it's still a bit foundational. And it's something that probably being in Vienna in the place of Boltzmann is quite relevant. A simple understanding, probably simpler understanding of what is called fluctuation relations, and put in a context of how to relate what we observe every day, irreversibility, as related to retrodiction. And I try to define this word. This is joint work with Francesco Buscemi and Clive O, who is my student. So, well, we all know what irreversibility or reversibility from everyday life is. It manifests itself in the sense that in some processes, if you were to watch the process played backward, you wouldn't see any major difference. So this would call reversible. In other processes, if you were to see the movie played backwards, you would clearly see that something is going wrong. And so these are what we would call irreversible, and that's the kind of, so the movie watched backwards makes sense or makes no sense. Now, if you want to assess these matters as a physicist, it's not enough to watch the movie backward. Why? Because physics needs the reverse dynamics. Now, I mean, we all learn in, as I said, this is mostly classical, right? But we all learn in basic physics that we have the laws of physics, essentially dynamical motions, and then there's the initial conditions that are free. And so the Newton law tells how things would move, how the planets would move around the sun, but you have to put the planet somewhere with some initial speed in order to see where actually it's going to be, right? So there is something that I would call free, I mean, in a sense, which is the initial state. Then the laws of physics determine the dynamics, and then you get a final state. So if you want to describe the reverse process somehow, in order to compare irreversibility and say how different these processes are, you don't need just to play the movie backward from this final state to that, but you need to be able to reverse the dynamics and to start maybe from another initial state. This could be the initial state. So what happens if I take the reverse dynamics, but I started the reverse dynamics with a full egg? What's going to happen to it, right? And this should be free. And it should be different from the final state above. In Bayesian terms, this would be the prior, this is a posterior, this is a prior. It's a prior for the reverse dynamics, it's not a posterior. So one question that was asked is this reverse dynamics determined also only by laws? Assuming that the law is these, right? So we've written down the physical laws for some reason, assuming that this is the arrow of time. The arrow of time is kind of assumed in this approach. We've written down the laws like that, and the question is, do these laws immediately determine the reverse dynamics? And the answer is usually no. And that's not a new answer. We refer a lot in our work to this person, Satoshi Watanabe, who in these very old years wrote a lot of what I'm going to tell you. And it has been cited decently by philosophers. It is vastly ignored by physicists. I think he has 120 citations, so most of us have many papers with more citations than that. But I hope that you read his papers and maybe cite it at some point if needed. Anyway, so I'm going to tell you what the point is. So what is the reverse dynamics? Well, there is a simple case which Watanabe called bilaterally deterministic dynamics. You can think of Hamiltonian dynamics, unitary dynamics, but let's say Hamiltonian against state, let's say classical for a while. So this means that something like that, right? So is bilateral deterministic, because deterministic would also be something where I send all the states here. That would be deterministic, but not bilateral. In that case, it would be with my next example, right? So this is a kind of bilateral deterministic dynamics, Hamiltonian channel, and well, it doesn't take a lot of fantasy to see what the reverse is. So if now I take the initial state as that, I just put the arrows in the other direction. And so the reverse channel, in this case, is fully determined by the forward channel, and it's actually the inverse channel of the physical one. By inverse meaning, well, that, right? That if I were to compose the two channels, it gives the identity. And I would say, well, thank you for the triviality. Yes, if you read the literature, you will find that these channels are typically described. I mean, this works also for Hamiltonians that depend on time, and typically many people in statistical mechanics study Hamiltonians that depend on time for a parameter. and you will find a tilde on the parameter because, so the parameter must evolve here from 0 to t, this from t to 0, so that's a minus, and then there's a tilde because you have to reverse some magnetic fields in case there are some things like that that do not transform well under time reversal. You need to parity as well. Now, maybe more interesting, I don't know if it's obvious for all of you, it took me some time to just digest it, but it's kind of also, that is if and only if. So maybe the second statement, it can be not so strange, right? That the only reverse channel that will be the inverse is this. But what's funny, this was proved by Watanabe, is that this is the only case where the reverse channel is determined by the physical channel. Any other channel you can think, the reverse will have to add an element that we call arbitrary. In a sense, arbitrary in the sense that is not determined by phi. You may have very good reasons to introduce that thing. So I will leave a question pending for a while in my talk, and the question will be, what is the reverse dynamics of this guy? This is a kind of erasure channel, where it's not an erasure because this is probability 0. I just invented one for graphical appeal. I could put any probability, but the idea of this is that any initial state is sent to that state, right? So I put the arrows, all the arrows with the same intensity p here, with the same intensity y minus p there, and 0 here. So whatever state you put in, this channel will give you that state, that mixture. So, well, what is the reverse channel? I will answer later, at least. Well, it's not the inverse of the physical one. Well, this one is not even inversible, right? Because it's all to one, so you cannot invert, so that's clear. And I told you, and I will motivate now, that it's not fully determined by it either. So they must have a free arbitrary element somewhere. What is missing? Okay, there are two paths to find the answer, and one is a subpath of the other. So the physicists, pretty much everyone in statistical mechanics have done this that I call reductio ad Hamiltonianum, which means you close the open system, right? The physicists believe, in classical physicists, especially also quantum physicists in the Church of the Larger Hilbert Space, they believe that ultimately everything is reversible. So what do you do? Well, you just, so these are my 3 states to the system here, and I add the bath, I tensor them, I have now all these states, and now we believe that the dynamics must be unitary, so this one will go here, 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 and so on. I didn't roll the arrows, otherwise it would be a mess. So now this guy is one of the channels I described before, and now I can reverse by inverting the arrows, I trace the path, and I got something that will look like a reverse channel on the system. Yes, this is systematically used in statistical physics. I don't know any paper in statistical physics. I have not read the whole literature, obviously, but I don't know any paper where this is not done like that. There are some shortcuts when the bath is thermal. There are some ways you can get around. And what is arbitrary? Well, arbitrary, you all know, right, is that this dilation is arbitrary. Again, what I mean by arbitrary is you may have a very good reason to say that I know that my bath is that type of bath and my interaction is that type of interaction, sure. But it's not determined by this thing. You're bringing in additional knowledge, right? There are different dilations that can give the same channel, and the retrodictions to the reverse will be different. Now, what I call the higher path is logical inference. So you just do the Bayesian trick. You later, this I will spend some time explaining. So you declare that there is a reference prior. You have a reference belief on your system, as in again, I guess some examples later. But as in you go to a sickness test, and the test comes positive. But what you really want to know is whether you were sick or not. In order to know whether you are sick or not, in the sense whether with a false positive or true positive, you need to know how widespread in the population the sickness is, right? So you need a prior. Once you have that, you just equate these things. This one is fully determined by the reference prior because the sum over x of this guy must be 1. So this is nothing else. This term here is nothing else than the sum over x of this expression. So the only arbitrary element is really this that appears also there. And okay, now you invert the thing and you get this beautiful equation that is so trivial that some of our colleagues has forgotten this term in some papers, but well, it happens. It has consequences. Why I call this the higher path? Because, you know, the Bayesians, at least the believers in Bayesians, will tell you that their way of reasoning must incorporate all the knowledge you have, all your beliefs. If you have a belief about the bath, you must use it. And if you use it, then you're back to what I had before, and then you invert in the usual way with a unitary thing, right? So so in a sense, what I did before is a special case of these, where your variables, you bring these variables to be, you say, okay, I have an additional belief in addition to my channel, I have the belief that there is this bath and there is this interaction, and therefore these variables now take the value of both the system and the bath, and you do a Bayesian retrodiction, which in that case is trivial, you just invert the arrows, on what you had. So in a sense, this logical inference is always happening. In some cases, it's kind of trivial when it's these bilateral deterministic channels. In other cases, you have other tricks. So quick recap of Bayesian inference just in case, and I will do it with an example. It has nothing to do with physics, which has something to do with my talk later. So this is completely invented by me, statistics of, and these letters mean women, men, non-smoking, smoking. So this would be a statistical population where I'm interested in dividing by gender the behavior of smoking or not smoking, right? And I have this initial probability distribution. And now suppose I give you an update and I tell you that, so I want to see the population that I'm going to meet, but I'm going to meet people in a no smoking place. Well, then you know how to update this probability, right? You remove the smokers and you scale up the other two squares in keeping the proportion, right? In equation, it gives you this. So what it means is you keep the conditional probability, given the updated y, you keep the conditional probability of x given y. And of course, now y has taken the value y star. Now, just something, what about soft evidence? So if I tell you that the place where I'm going to be is not too friendly for smokers, and I have a reason to believe that, I don't know, only 70% of the smokers will be there, then I will get something like that, right? So the smokers will be still there, but a bit squeezed, and the others must be a bit big. The total must still sum up to 1. And the usual update in such a way that the ratios are preserved between these squares and these squares. Sorry, this ratio is the same as this ratio, and this likelihood is the same as this likelihood. And the update is just done more or less as before. So you keep the conditional probability as a belief, and you multiply it by the new prior. The new prior being the new belief that now the smokers will be only 70% of the prior one instead of 100% of them. This is called Jeffrey update. That is usually, it has a name. It's called Jeffrey's rule of probability kinematics. For those who are into Bayesian things, it's not the same Jeffrey as the Jeffrey's prior. That's a different fellow. That are S at the end. This is Jeffrey, is a philosopher. The other one was a mathematician in Cambridge, and is compatible with what's Peirce's method of virtual evidence. Or also James has this idea. Well, it's essentially a process. I can explain this later. So you can derive it if you have a process that the variable x influences the variable y, and only y influences z. Then this is the Bayesian update that leads you here. This is the case in my example, of course. In my example, the place was not too friendly for smokers, but had no constraint or change of probability regarding the gender, right? So if I had also added that, then the Z would have influenced also X. That's the kind of reasoning there, right? But there I just said it's not too friendly to smokers, but men and women are not affected by whether this place is, what the place does, right? And so you have really this logical chain, gender, smoking, and then whether you want to enter that place or not. Anyway, so this is the kind of formula I used before. So I have the channel and a new prior that that I can now multiply in order to get any answer. So what is the reverse channel according to my recipe? It's not such a surprising answer once you see it, but People tend to think, oh, it's a completely random thing. Why? Because I destroyed all the information here, so then here must be completely random. It's not exactly that, almost. The reverse channel is the erasure channel that sends you back to your reference prior. It's not completely random, it's your initial belief. Right? Of course, all the information has been destroyed, so you can't hope to get anything really meaningful here. But what it does is that any state you send in, it will tell you, well, your initial belief was correct, right? Because you believed it's correct and you have no evidence that it is not. Quantum, finally. Something quantum. So what happens if this channel is quantum inside? So it means that this variable x prepares a state rho x, goes to a CPTP map and gets measured by POVM here. This is the outcome of the POVM, so that's the channel. Well, the reverse is also quantum. And the quantum inside, if I plug in my formulas, you get these kind of beautiful things. Kind of a mess, right? All these square roots and... but essentially what it means is that the input state is determined by the POVM, the output state is determined by the initial state, and the most important thing is the channel is the PETS map. So this is a PETS recovery map that is used even in black holes, right? Even in black holes, when they do the error correction with the black holes, they get PETS maps. But of course, it's mostly used in quantum computing, and one of the speakers here has rediscovered that after PETS invented it to study the properties of the relative entropies in 1970 something. And this has been called, on formal grounds, this has been called quantum retrodiction by people like Leifer, Speckens, Fuchs, others. But here, they didn't do this reasoning. So here it really appears that if I take the classical channel, I go through the Bayesian retrodiction of the classical channel, I see what's inside, I get these kind of things with the PETS map appearing naturally. Okay, so now, well, we have some arbitrariness. Which reference priors to choose? All of statistical thermodynamics ends up choosing the steady state of the channel. Well, which is of course in general different from thermal equilibrium, because, well, there's no thermal bath, right? And the rationale, of course, is physics inspired. In a sense, it's like, if I take a process where I see nothing happening, well, I don't know if it's happening forward or backward, right? So because nothing is happening. So that's the idea of taking the steady state. For those of you who are a bit more game-oriented, you may think of something like minimizing the expected statistical distance between prediction and retrodiction, and then, funnily enough, you don't get the steady state, you get the uniform state as the reference prior of choice. But this has not been used by anybody. We just found this result recently, and as far as I know, this has not been practiced. And this one can be a steady state only for bistochastic processes. Now, here comes a quite an important thing. Here is what I've told you. So you have to think, I think that like often in our field, it's good to think of these things as a game between a predictor and a retrodictor. So there is a referee, and there are two people, Alice and Bob. Alice has to predict, and Bob has to retrodict on a given process, right? And the referee, what is the referee going to do? The referee is going to give some distribution to Alice, and Alice has to produce some outcome, and he's going to give some distribution to Bob, and Bob has to produce some outcome. And then we'll see if they do agree in a way or another, right? Now, the point I want to make is that, you see, the reference prior is a bit like local hidden variables in a Bell game. So it's something that Bob must invent before the game starts in order even to be possibly able to retrodict. Otherwise, it doesn't even need the channel. Okay, so Bob at some point decides, okay, I have to retrodict on this thing. The laws of physics are on the side of Alice. I have to invent something. I believe uniform prior, whatever. Okay. Then the game starts, and of course the referee can send any prior to Bob, to Alice, and any prior to Bob. The referee doesn't need to sample X and Y according to the reference prior. That's a kind of important remark, because that comes in play here. So what we call the forward process, usually, or the prediction, is the channel multiplied by the prior that the referee is using. And what we call the backward or reverse process or retrodiction is the channel reversed with its reference prior embedded in it, but multiplied by whichever prior the referee chooses to use, which may be completely different, depending on the game. Okay, this is the kind of formalism. What I'm going to do with this, let me tell you something funny. Okay, this thing is called entropy production. I may say, why? Bad news. I cannot prove it. Why? Because I can define that ratio also for the gender and the smoking. And what is entropy production in the case of counting how many women smoke, right? So this must be something model related somehow. You find this formula in every review on statistical mechanics, formula number 1 or 2, at best 3, okay? So entropy production is defined like that. Is valid by inspection in model of statistical thermodynamics. Langevin Brownian motion with 2 forces, 3 thermal bath, comes out like that, okay, whatever. It's beautiful though, because if I take the average of this thing over the forward process, I get the statistical distance between the forward and the reverse process. So you get a statistical comparison between these two. That sounds like something you would like to do with entropy. Actually, well, between prediction and retrodiction of the same process in my language. And well, this is what? This is the change of entropy macroscopic, right? X and Y are the microstates. And now I take an average, for me, the one who sees the physical process, which is this one. So the change of entropy, and this quantity is known to be positive. So, well, I mean, you get this formula, at least you get the second law thermodynamics for free, right? It might be an advantage. And again, it seems that in statistical thermodynamics, everybody uses it. Really, I'm very honest with you, maybe some of you knows the answer, but I haven't found, so you go into these papers, you find which references are cited for this formula, 1, 2, and 3. And these are 1980 papers where they do some Langevin Brownian motion. And since then, it's the general formula, right? Or whatever, but. Okay, now you say, well, where does Bayesian retrodiction enter here? Well, that's cute. So this thing, so the reverse process is a Bayesian retrodiction of some type, if and only if this entropy production has this form. So it means that you can compute entropy production by taking a function on the input state and a function on the final state, possibly different functions, not necessarily the same, actually, but they're written here. Okay, I don't know if, this might be very deep. At this point, I don't know. Why I say it might be very deep? Because if this is really entropy production that the formula I had before, then we have a connection that says something, you know, typically when people discuss thermodynamics and logic, they tell you something like, the Shannon entropy is equal to the thermodynamical entropy for some ensembles, not from others, and then Arrhenius entropy relevant for thermodynamics, yes, no, information, non-information, Peter Henke versus Toffoli, and here it would be just like, you know, forget about, I don't know what these functions are, but if I want entropy to have this form so that I can compute it on the initial state and on the final state without having to compute the correlations, well then the way I define a reverse process is Bayesian, is logic. So it's a bit deeper than discussing on the, but again, it might be, I mean, it's based on that formula of change of entropy that I can only justify with a bit of hand waving and some Langevin motion. And let me finish with the famous fluctuation relations. For those who don't, you might have heard at some point Jarzynski equality in your life. Let me tell you what these things are. And I will show you how the formal derivation is really what I would call trivial. And then it's nice because we have a trivial formula in which we can plug physics. That's the way we do it, right? That's not the way the papers are presented. These things are derived usually. So let me start. I want to study the distributions of this variable that I defined this for obvious reason with the analogy of the previous process, but just two distributions, P1 and P2 of variable Z. Well, the distribution of this variable for an observer that samples for P1 is this, right? So with probability P1, I draw Z, and then in that case, the value of omega is omega of Z. The distribution of P2, of course, is the same kind of thing. And now, as my Swiss-German teacher in EPFL used to say, personne peut m'empêcher, which means nobody can prevent me from writing these. Of course, all these probabilities are all non-zero in all the elements, as usual. If you have a zero in a probability, take 10 to the minus 200, and I challenge you to find the difference. And then here, because I chose the variable like that, that's my variable. So I got this beautiful thing. So, well, who cares, right? And then I can even do something more that you don't care about, which is to integrate over omega. On the right-hand side, I have the average value of this guy over the mu1 distribution. On the left-hand side, I have 1, because this is really supposed to be normalized. And again, who cares? Well, this is the mathematical structure of Crooks 1998 and Jarzynski 1997. That's how they look like. That's the proof. Nothing else. In particular, if Jarzynski equality must have a 1 on that side because it's a normalization of reverse process. Anyone who violates Jarzynski by putting a different thing here, it means they've not normalized the reverse process. That's what happened when I told you before that people forgotten the gammas. Let me just, for finish, last slide, I derive the Jarzynski-Crooks standard one. So you put a physics process here. What is the physics process that Jarzynski considered? Prepare a thermal state for an Hamiltonian H0. Then there's an evolution. The evolution looks like that. The Hamiltonian may vary with time. It may exchange whatever with the bath. It's out of equilibrium, this thing. And then there is an assumption called micro-reversibility that don't ask the people with statistical mechanics what it means, because they have all different opinions about that, but I will tell you what I think it is. And then finally, you post-select, or you wait for the system to thermalize. They have a kind of strange language there that I'm also not mastering yet. You post-select the thermal state for the Hamiltonian at the final time. Okay, that is my beautiful formula, right? Remember, the logarithm of this is supposed to be what I want to fluctuate, or the entropy production. Okay, let's go through this. Okay, prepare thermal for H0. That's not difficult, right? I prepare thermal for H0. That's the normalization. Typically, the normalization is the free energy is the logarithm of the partition function, right? So that's where it appears here. Thermal for HT, same. Now, micro-reversibility, what's that? Okay, in our analysis, we came to the conclusion that that is the choice of the steady state as reference prior. And now remember that the ratio of these two was the ratio of this gamma and the gamma hat, but this is a steady state, so it's the same. So here is I replace this ratio by that formula. So in my language, I choose the reference prior as the steady state. At least I know what it is. Now the exchanger with the bath, and I need the steady state. And what is the steady state? You're interacting with the bath that will take some heat out. So the state that remains steady is the one that somehow had the same heat that is going to be exchanged, right? That doesn't change that thing. So it's something of that type. Is proportional to the heat that is going to be extracted by the bath. If you put it in at the beginning, it will not change too much. So then you get these. And this is this, and this is that. So this is the difference of energy. This is the heat that has been exchanged in the process. This is the change of the difference in free energy. And so the logarithm of this is the variable I want to fluctuate is work. And really now you go back to my previous two equations, you plug this thing in, and that are really the Crooks and Jarzynski equalities as you find them in the paper. But at least here I think we have decoupled the mathematical structure. You know, you may always wonder if you read some papers in this field, you wonder why the fluctuation relations always look the same, okay? People have processed all kinds of things, Hamiltonian driven in crazy ways, multiple thermal bath, non-thermal bath, and at the end, it's always exponential my work equal to 1. So why? Well, because of that, right? Okay, let me finish. So what we did is we just wrote some margins, some notes in the margins of Watanabe's paper. At the time of Watanabe, there were no fluctuation relations, or at least there were only the linear response theory, like the fluctuation dissipation theorems. These are more advanced, the ones I proposed. The others can be derived from those. So this is the first paper, Reviews of Modern Physics, 1955, Symmetries of Fields, Prediction and Retrodiction. It can be shown that the actual success of a retrodiction depends on the satisfaction of an additional condition which is not required in prediction, namely the reference prior. This is more beautiful. It's more provoking also. The second paper, this one you can download. You Google Watanabe 1965 condition probability in physics, you can download a PDF. It is contended that the phenomenological one-wayness of temporal developments in physics is due to irretrodictability and not due to irreversibility. This irretrodictability is shown to originate from a simple property of very notion of conditional probability independent of the structure of dynamical theories, namely that you need a prior in order to... It is demonstrated how macroscopic irretrodictability can be reconciled with microscopic irretrodictability in classical physics. Quantum physics is irretrodictable, microscopically as well as macroscopically, and this was the debate at this time, whether it's invariant for any combination of symmetries. So, summary. Okay, we formulate physics according to our perception. So I have a perception that the process goes from X to Y, whether it's correct or not. Well, correct in the eyes of God, let's say. Maybe it's not my problem. Then what I told you is that having formulated physics from X to Y, going from Y to X is usually more arbitrary. There is an element there that you can't do without adding this arbitrariness. And entropy would capture in this view the statistical asymmetry due to this logical asymmetry. Of course, there is a huge problem with this approach. I am the first one to recognize it, is that I can't attribute the degrading of my knees that prevent me from playing soccer to retrodiction. It's really, it's not that I can't remember how many games I played and therefore now I cannot play anymore. It's really the knees are aching, okay? So more seriously, if a city has been bombed, you can say, oh, it's just retrodiction, right? I mean, the bomb has come down. And so still to connect, I'm not, Francesco Buscemi is, I'm not fully bought, let's say, to the camp of thermodynamics is only logic, is only thinking. For me, there is some physics going on there. I have not yet found exactly how to combine it. And that's the end of it. Thank you for your attention.
Czaslaw has a question.
Thanks, Valerio, for the talk. I want first to share the feeling that you expressed in your talk. I also recently looked at these things that are not in my field, and I really didn't understand why they call this entropy production for, in your notation, delta S XY. And you see that it has something with a measure of distinguishability between the forward and the backward process in their language. And when you average in some special cases, when you average this, then you obtain the one, the difference. And so it's very encouraging that you show necessary and sufficient conditions. That's one thing. And then the other thing is what I would like to ask you. There is this problem with, I think Tony has a paper on that as well, is in this, how they actually evaluate the entropy production is to, in the standard approach, is to measure the work performed in the process, because the entropy is then defined as a difference between the work and the free energy. And then in order to do so, you perform the measurement of energy before and after the quench, from where your system drive out of the equilibrium. And then this is fine. And then there is kind of criticism of this approach is that by measuring the energy, you destroy the coherences between this and you influence, in a sense, the process. And then there is an attempt to define work not through the measurement of energy. And then Tony has, I think, a paper of some kind of a no-go theorem that you cannot satisfy certain conditions. He knows better. So what I'm asking you, can your work shed some light on this problem, or how?
It nullifies the problem. Any state, any channel, any measurement. No need to pre-measure the energy, no need to post-measure the energy, no need for the channel to preserve any energy. So yes, it has been a debate in quantum information to generalize. That's where we started from. That's why I started working on this, not because I wanted to understand statistical mechanics. It's because Francesco brought to my attention some quantum problems, right? Before our work, there was a kind of paradoxical situation that the Jarzynski equality and these kind of things were valid more generally in classical than in quantum physics, right? Well, nobody would expect the opposite, right? We expect that. And because for quantum channels, if it's not unital, my goodness, right? Everything, hell breaks loose if it's not unital. Well, if this channel is not unital, you cannot forget this term. And that's what all our colleagues were doing. End of story. So my answer is, that problem is no longer a problem. You want coherence, you put coherence. You want to preserve it, you preserve it. Nothing to destroy. So the two measurements of Tazaki is what is the first attempt to do something in year 2000. I mean, 3 years after Jarzynski, he came up with that. So it's a great step. But everybody after that, they started with this two measurements thing. For this, formalism is not needed. I'm not speaking here, of course, of the famous problem of defining work and heat and this kind of stuff, right? There you may have to measure something, but for the fluctuation relations and all these things, everything goes through without any problem. So yeah, I think that those debates, at least the ones, that specific question, I would say, has become a no-brainer.
Thank you.
Probably our contribution.
Renato?
Okay, thanks, Valerio. That was really great. So you remember yesterday I told you without knowing what your talk is that I also don't understand the entropy production. So it's good now to have heard your view. That was really very useful. I just have a small question that relates to your example with the egg. So you mentioned, and I think there you didn't give a deep reasoning, that people are using the steady state usually of the channels in all these arguments. Now, if I look at the example of the egg, that would be a very unnatural thing to do because, I mean, our prior is usually that when the egg is laid, it's kind of probably a full egg that is not broken. So we have this prior. So it would be very unreasonable to take the steady state, which is probably a broken egg. So how would this view of taking the steady state relate to your introductory example?
I think that the answer is here, if I find again, so my eyes have gone, apart from not playing soccer, also I need some spectacles sometimes. For the young people, you see that there are some problems with age. Huh? So I think that's the problem of the egg, all right? So if you have a situation where at the end the result is destructive, right? Wherever you throw the egg, that looks like the same, more or less, right? Then the reverse or the retrodiction would be like, what did you believe the egg to be? If you believed it was integer, well, any shattered egg will be retrodicted to an integer egg. If you believe the egg was already shattered, every shattered egg will be retrodicted to that part. So this channel is so destructive, this mathematical one, so that's the closest approximation I can make to the one of the egg. This channel destroys the whole information, right? It's an erasure channel. So therefore, you can't, I mean, it's kind of rational that when you retrodict, you destroy also the information, right? It would be crazy if it would not be the case. And you end up to what? To your initial beliefs.
But that's not the steady state then.
No. It could be, but it could be the steady state. You could have chosen this gamma to be the steady state, and then you would retrodict to the steady state, whatever that is, right? But I could have chosen another one.
So you have a choice of
right.
of
now,
what?
in statistical physics, I have to say that again, I have to confess my laziness. So once I've understood things in this kind of compact way, right, I'm a bit lazy now to read back and to start reading all the 20 years papers and say, oh, okay, now this one has used this assumption and this assumption. When I combine these two assumptions, I get this thing. So, and they don't speak in Bayesian language, so they don't tell you we choose the steady state as prior. They tell you they have micro-reversibility, and then they tell you it's very reasonable to assume that, and it's usually assumed that the other one also. What we found is that when we try to reproduce many of these fluctuation relations, again, not all, we don't have time to, in our formalism, the compact way of doing is to choose the steady state as reference, and then typically the thermal priors are always chosen, and the difference is really what the steady state is. In Tasaki, for instance, the steady state would be uniform because he assumes Tasaki 2000, the quantum one with the two measurements of energy, he assumes also a unitary development. If it's unitary and projective measurements of energy at the end, then the steady state can be uniform, and then you get the ratio of the ratio of the thermal states. Yeah, all this is work in progress, right? So maybe next year I will tell you that no, we found something that is a bit different, or someone who didn't use the steady state. But that's my current understanding, is that to recover the traditional results, you need to make that assumption.
Thanks.
More questions?
It's a coffee break looming, so I think.
And no online questions? Okay, then we can, yes, there is an online question.
Well, let's see who shows up. Yes. Feel free to start.
Yeah, so the online question, I can take it away. It should be there.
Do you hear me?
Yes.
Yes, please.
Okay, I have questions about detailed balance and time reversal invariancy. Okay, if you look at the very classical perspective, if we say a system is especially a stochastic process that is a detailed balance, then it should be also time reversal invariant. But if you come to the when we come to the quantum physics, especially the definition of the time reversal operation in the quantum physics, for example, the one given by the Jarzynski-Crooks in his paper 2008.
Yep.
These two terms doesn't seem to be compatible with each other. For example, if you take the quantum time reversal operation of the Jarzynski-Crooks, then you cannot connect these two terms with each other. So
okay, so the paper of Crooks that you mentioned is one of the papers that
the 2008 paper.
Yes. He anticipates some of our work by essentially the map he writes for this, what he called the quantum detailed balance, is the PETS map that I've written here on the screen. If you can see my screen, I don't know if you can see my screen, where the gamma zero state he chose as the steady state of the channel. So if you put this epsilon of gamma zero equal to gamma zero, so that these things are equal, right? You will find that this is exactly the channel that Crooks 2008 uses. So he somehow anticipated this formalism, but essentially assuming that the reference prior generates. In my language, the way to recover these would be that you see here that you would have to choose your classical reference prior and your input state of the quantum process in such a way that this guy is the steady state of the quantum channel, and then this expression would become the one that Crooks uses. So it is a special case of what we have done that you can certainly find. That's all I can say. Now, I haven't studied the philosophy of detailed balance, so I cannot pronounce myself on whether what Crooks defines as detailed balance deserves to be called detailed balance, if it's the same as in classical. I'm sorry, I'm not proficient enough, but definitely the Crooks channel is exactly that.
Yeah, I know. I mean, in his language, I mean, the formalism he derived, in his formalism, these two terms cannot be connected with each other. I studied a little bit more on the paper, and I recognize that these two terms in classical area, in the stochastic processes, we can connect to teach these two notions to each other, as I said before. But when it comes to the quantum realm, and the quantum time reversal operations, like the Crooks defined, we cannot connect these two terms with each other. I mean, in this formalism, you said, they are completely independent from each other. So it seems quite, it's inspired me that, I mean, the way of defining the time reversal of the Crooks is not quite what can I say, trustable.
Well,
I'm sorry, I'm using
look,
this.
all I can say is a right to Crooks, right? I think my way, I understand my way of presenting retrodiction, and I think it's Bayesian retrodiction and is as logical as it gets. If Crooks did not argue, I'm not an exegete of Crooks, so I don't remember that paper in detail, all that he has written, how he has justified his moves. If it's not satisfactory, well, it's probably not up to me to say it or to comment, right? I mean, maybe we can discuss later if you want by email, but if you have anything against Bayesian retrodiction, you can challenge me. If you are fine with Bayesian retrodiction, then you should be happy with what we have done.
Okay, thank you very much. Thank you.
Welcome.
Thank you.
Okay, thanks. And let's thank our speaker again.